Alright. So I see we've moved back from legitimate instruments like the flute to hillbilly instruments. He's got a pair of spoons, folks.
Are you making fun of me?
Pair of spoons.
Spoons are an amazing
Look, you
instrument.
dragged me in here at
Watch bluegrass?
6:30 in the morning to do a podcast. I haven't had any coffee yet. You're breaking out spoons, of all things. I'm going to drink some coffee.
No?
No.
All right, maybe I'll work on that day
we're
job
going to, again, stick in the chemistry here. This is podcast 4.3. We're going to talk about redox, oxidation reduction numbers, and balancing oxidation reduction equations.
Isn't that a cool picture, Mr. Sam?
It is. I love the rusty car.
It is an old rusty car. In an oxidation reduction, of course, what we do is we're going to talk about rust is one of the things in an oxidation reduction reaction.
My son's a big fan of the Cars movie. He likes
the
Mater.
Cars movie.
Mater's a rusty old tow truck. Yeah.
I have no idea what you're talking about.
You've never seen the Cars movie?
I don't think I saw that.
Oh, that's great. It's a little Disney movie.
I bet it is. Okay,
yeah.
well, let's just chat in here. Oxidation reduction reactions are reactions we've not talked much about. In fact, I don't know if we've ever talked about
I don't think
that.
we talked about them in general chemistry.
No, we didn't. But now we're going to. Now, oxidation reduction reactions are reactions that involve something called oxidation numbers. So before we can really talk about what an oxidation reduction reaction is, we have to understand how to do the oxidation numbers rules. Every element in a compound, and actually even an element in its pure form, has a oxidation number, and there is a set of rules whereby you assign an oxidation number to a particular number. And these are the rules.
Yep.
Oxidation states, if you have a pure atom, it has an oxidation state of 0, like a 0 charge. It's kind of like charge, but not exactly the same.
Kind of.
Yeah, ions keep their charges, so if you have sodium or whatever, because it normally has a positive charge, then you leave it with a positive charge. Duh. Oxygen typically in a compound has a charge of -2 unless it's peroxide.
Very rare.
And that's -1, very rare, yes. Fluorine is always -1, unless of course you have F2, and F2 is the elemental, and that would have a charge of 0. Hydrogen is +1. In case of very, very few exceptions, when you have the hydride, I don't know that we even talked much about hydride, and that's not a big deal.
They're not going to encounter them in our class.
And the sum of oxidation states for a equals the charge of the substance. If it is a compound, then it's 0. So we're just going to do a number of example problems here.
Those rules are all in your handouts. If you're out there in internet land and you don't have our handouts, just hit pause, write them down, learn
Copy them down.
Yep.
So let's do a couple of examples and see if we can make this work. So I am going to choose the compound sulfur trioxide.
Okay.
All right. We want to assign oxidation numbers to each element in sulfur trioxide. So
Yes.
Mr. Sams, what are we going to do?
Well,
here?
oxygen's always -2.
Yeah, so O is -2. So O is charge. It's actually its oxidation number is -2. And then the sulfur, we have to just sort of add them up. It's just mathematics. So it's going to be -6.
Because we have 3 oxygens.
Yeah. So and this is a compound, so compounds add up to
0. There's no charge.
So what must be the charge of the sulfur?
It would have to be +6.
So yeah, it's like I like things X - 6 = 0, and this is not hard. So the S has a oxidation number of +6. Now let me talk about this for just a moment. The reason when you write O -2, that actually indicates its oxidation number. If I say O2 negative, what that means is it means that this is actually the charge. A-R-G-E. So the charge is, you'll say 2 minus or 3 positive or whatever, and the oxidation number is plus something. So it's a minor point, but not too terrible. Can you think of another one we ought to do?
Let's do something with nitrogen in it. How about NO2? No, let's not do that. Let's do nitric acid, HNO3.
Nitric acid, HNO3. So nitric acid. Now, what's the story on hydrogen?
Hydrogen is always +1 unless it's a hydride, which that's not.
And then the nitrogen's the tricky one. Oxygen is always that negative. So I'll say +X. Plus, and O is, of course, the -2. And there's 3 of them, so that'll be -6. And this is a compound, so it adds up to
0.
So 1 plus X
It's going to have to be a +5.
So X is +5. So you would say H +1 in +5. So there's always sort of one that's kind of hard to figure out. And the rest?
Yep.
Well, the rest are
So
not.
the ones that you know that are always something or usually something, do those first, and then things that can have multiple oxidation states. Nitrogen's weird, sulfur's weird, manganese, a lot of those transition metals can have multiple oxidation states, so you do those last.
Okay, let's do one that has a charge. How about perchlorate? ClO4 -1. All right, Now this one's a little bit weird because we know the charge is -1. Actually, what should I actually say instead of -1?
Should say 1 minus.
I should probably say 1 minus because that is the charge. So which is the one that's known?
Well, we're going to know oxygen, which is -2, and there's 4 of them, so that's a total of -8.
So x minus 8 equals what?
-1.
This one is a little tricky. Instead of saying it equals 0, it equals -1 because it equals the charge. That's the rule. So of course x has to be
+7.
X is +7.
Making me do math before 7
I
o'clock.
know. This isn't a very mathematical lesson. Cl plus 7 O -2. Now, to make a note here, chlorine doesn't really have a charge of +7. It has an oxidation number of +7. You probably memorized that chloride has a charge of -1, and that's correct. So you're going to do lots of examples in book problems, so I think that suffices for what we do. Let's define some terms here. Now, in an oxidation-reduction reaction, something is oxidized and something is reduced. Now, the best way to remember that is there's this saying about this lion, and the lion's name is Leo. You say Leo. Says
No, I also learned oil rig, which is another one.
It means lose electrons. Oxidation. It's hard to write it down like this. And then gain electrons in reduction.
And I learned oil rig, and that's just oxidation is losing, reduction is gaining. But it doesn't refer to electrons, so if you forget what that is, Leo says Gary helps you a little more.
Now, another thing I like to think about when I think about the definition of oxidation, actually, let's go back to this screen. Oxidation, of course, is where a substance gains, right? Hold on.
Gains charge. So it's losing electrons.
Lose electrons, and this is gain electrons. But I also like to think of as oxidation. What's happening, kind of, if you think about it, it's going to gain a charge. Actually, it's going to gain an oxidation number, but they're very similar, so it's easier to think of a charge. And then, of course, reduction loses charge. And I like to think the fact that, definitionally, that when you lose a charge, it's reduced. That just kind of makes sense.
Yeah, you get more negative is what you end up doing. So that's how I think of it, as being reduced. You get more negative.
Then we have these odd things called oxidizing agents and reducing agents. What's up with that, what you're saying?
Well, oxidizing agent, that's the thing that gets reduced. No, that's right. It gets reduced.
Huh?
You're thinking, why did... Well, the thing, if it gets reduced, that means it did the oxidizing. Because it went out and it said, okay, your charge is going to go up. And by doing that, its charge had to go down and got reduced.
So the thing that's reduced is called the oxidizing agent?
That's correct.
So that must mean that the reducing agent is the thing that
gets oxidized.
Gets oxidized. Okay.
Yes. So if it gets oxidized, it does the reducing.
So it's kind of a weird thing.
It is.
Ladies and gents.
You just
gotta
gotta
just sort of
know it. Yep.
All right, let's take a look at this example.
Yeah, that should not have the SO2 at the end.
Yeah, it doesn't on your paper. So we had a mistake on our PowerPoint here. Okay, here's what we need to do. We need to assign oxidation numbers to every element in this particular chemical reaction. So here we have lead. Now, what is the elemental charge on lead? I'm looking at the periodic table. It looks to me like it's +4.
Well, that's just a pure element right there. There is no charge on it. So pure elements always have an oxidation state of 0.
Don't forget, ladies and gents, that's perfect, that lead has a charge of 0 when it's an element. And oxygen, I usually think of oxygen, we just learned, is -2,
Yeah,
right?
but right there it's in its elemental form too. It's not in a compound, so again, 0.
All right, now when we look at it in a compound, ladies and gentlemen, what we need to do, of course, here the oxygen does have that charge of -2.
Yep.
And then the lead, of course, to balance it out, it's just PbO. It'll be +2. Now let's take a look. The lead is going from 0 to +2.
Yeah.
So that's going up in charge.
Yes.
0 to +2 is up.
So that got oxidized.
So this is oxidized.
Which makes lead, strangely enough, the reducing agent. Because it got oxidized, it's the reducing agent.
So it's the reducing agent, okay? Now, we'll look at this, but yeah, you'll see this. O goes from 0 down to -2. So if he's reducing down, he's therefore being reduced.
He got reduced, making him the oxidizing agent.
Now, I want you to understand, ladies and gents, that something I was going to say and I just lost it. It's early in the morning. It'll probably come to me as we do the next example. Okay. Okay. This is a very interesting problem.
Oh, yeah.
I like this particular problem. So let's assign oxidation numbers. Here's the chlorine. I think I've learned this now. It's an element, so its charge is 0.
Yep.
The oxygen in hydroxide is
-2.
-2. the hydrogen
Plus
is
one.
plus 1. Actually, I do remember what I was about to say. Something you understand, guys, is that in an oxidation reduction reaction, only one thing can be oxidized and only one thing can be reduced.
Correct.
Something goes up and something goes down.
Right.
You can't have two ups, two downs.
Nope.
You can't have two ups and a down. It's only one up,
One up,
down.
one down. Reason being, guys, the whole deal behind oxidation reduction reactions is electrons are being transferred from one element to another element, and they're only going from one thing to another.
So it's a transfer. Perfect.
Yep.
All right. Let's do this chloride because this is easy.
That's nice and easy. That's
Negative 1.
-1 because it says
And
-1.
the hydrogen here is
Plus
positive
1.
1, and the O is negative 2.
Minus
My
2.
O's have not changed, nor my H's at least yet. Now, what's going to be the O and the ClO negative?
O is going to be -2.
Minus 2, and then when you do the math,
They have to add up to
X
-1.
minus 2 equals negative 1, so X is
+1.
plus 1. Now, we have to look for elements that are changing.
Yeah, it looks like the
Now-
chlorine went from 0 to +1.
Okay, so if it's chlorine going from 0 to plus 1, it is being
Oxidized.
going up, so the chlorine is being oxidized.
Now, wait a
I need
minute.
to find something to go down. So now the oxygen is going from -2 to -2.
Yeah,
So that's not a change.
that
Okay,
didn't
so it
change,
must be
no.
the hydrogen.
No,
the
no.
hydrogen is going from positive
No.
1 to
No.
I thought
No.
we just said that something must go up and something
It
must
does,
go down.
Mr. Berger. Look at the chlorine again. It went from 0 to -1, in addition to going from 0 to +1.
Oh, okay. So guys, what's going on here is the chlorine is also being reduced. This is a situation where one chemical is both being oxidized and being reduced. This does happen. In fact, it gets a special scientific sounding word.
Disportionation. Or something like that. Is that right?
I think it's pronounced disportionation, Mr. Sams.
Portionation? I don't know either.
It's
It's just big and
disportionation,
obnoxious.
and I've spelled it right.
Man, these are boogers.
Yeah, I know.
When you get to predicting products, I always mess these up for some reason. So when you're struggling through them, just know that Mr. Sam's always messes them up, and it usually takes him about 4 or 5 tries to actually get it right. Bergman gets them right on the first try.
I'm amazing.
He's been doing this a lot longer than I have.
Okay, balancing redox reactions. We're going to learn how to balance them. You know, when we balanced reactions in the past, you just kind of guess and check. That does not work
Negatory.
when you do a redox reaction.
Which is kind of nice, because personally, I like systematic ways of doing things. So balancing redox, you do the same thing every time. You get the right answer every time if you follow the rules.
And so these are the rules. First of all, you write something called the half reactions. The half reactions, one will be the oxidation reaction, one will be the reduction reaction. You balance all the elements except H and O. You balance H's with H positive, very important. O's with H2O. You know what? This is backwards.
Kind of in the back, yeah, in reverse order.
Usually you should
Yeah.
do this in the opposite order.
Yep.
Then you balance the charge with electrons. It's best to watch me do this. Multiply reactions by factors such that the electrons cancel, and then you add both half reactions. It's best to just do some examples, and so we're going to dive into examples. This assumes, by the way, that you are in an acid solution.
Yes,
right?
and if it doesn't say otherwise, you're in an acid solution.
So yeah, acid solutions are assumed here, and so now we're going to do these examples. Another thing I want to make a note of is that it's best to center everything on the page. And so I'm going to put my arrow in the center of the page, and I kind of build out from there. I'm just going to recopy this so we have a white screen. It's easier to do this. So let's start, and now I do not actually try and figure out what the charges are, or the oxidation, but I kind of see the iron is going from a 2 to a 3.
Yep.
So this is going to be one of my half reactions. I don't even bother figuring out if it's oxidation or reduction, unless the question asks me to. And so I'm going to say Fe2 positive goes to Fe3 positive. I'm kind of center this on the page.
Right.
Now I need to then follow my rules. It says write the half reaction. I did that. Balance all the H's with H positive.
Well, balance all elements except H and O first.
Oh, pardon me.
So there's one iron and one iron,
Irons
so
are
that's good.
Yeah. All
Balance.
right. Well, actually, switch this over.
Yeah.
I might switch it on your paper. Balance the O's with water. There's no O's.
No O's. Balance.
No H's.
No
This is
H's.
balance.
Yeah, but step 5 says balance charge
Oh,
with the
yeah.
electrons.
So the charge on this side is +2. The charge on this side is +3. That is not balanced. And you can only add electrons. Now, what charge do electrons have, Mr. Smith?
-1.
So if they have a negative charge, I need to make the charge go down. Which side would that be?
I'm going to put it on the right side.
Yeah, on the product side. And we need how many electrons?
Just one.
Just one electron. And that is the balanced half reaction. It's being oxidized, actually.
Yes, so now the charge is +2 on both sides if we add it all up.
Yes, so then now both +2. Now let's do this next side. And then we're going to say permanganate, MnO4 negative.
Yep.
And that goes to Mn2 positive.
Yes, so this is the second half reaction.
Now balance everything except for oxygen and
Yep,
hydrogen.
so manganese, one of those and one of those, so we're good there.
We're good there. Now
Okay.
I need to then balance the oxygens with water.
Yep.
So I'm going to put in
4 waters on the right.
Now, why 4?
Because there's 4 oxygens there on the left.
Yeah, if you have 4 oxygens, each oxygen contains 1 oxygen. Each water contains 1 oxygen. Therefore, you need 4 waters.
Yep.
Now we've just created a hydrogen problem. Mr.
Yes.
Sam.
Now we have 8 hydrogens on the right, so we need 8 hydrogen ions on the left. Now you might be thinking, well, how can you just stick hydrogen ions in there? Remember, this is in an acidic environment, which means 1, it's dissolved in water. 2, there's hydrogen ions floating around.
Yeah, so there's acids involved in this.
They're just hanging out there, and then they go, hey, I think I'll be part of the reaction. So they jump right in.
All right, now we have a charge issue now. Of course, the charges aren't balanced. This
Nope.
side has a charge of, now
Plus
think of this,
2.
+2 for the manganese and 0 for the water, so a total charge of +2. And this side has a charge of, now there's a +1 here, but there's 8 of them, so that's +8. And then this has a -1 charge, so that's -1, so that adds up to +7. So if you've got a +2 on one side and a 7 on the other,
We're going to need 5 electrons on the left.
5 electrons on the left. Now what we need to do is we need to add these reactions such that the electrons cancel. Now I see I have 1 electron on the left, on the right side for the iron compound, and then 5 on the other side. So what I need to do is multiply one of the reactions, or both of them, whatever it takes, to get the electrons to cancel.
Yep.
So you're looking for the lowest common multiple between 5 and 1. Well, guys, that's 5.
Yep.
So if I multiply this by 5, this number here becomes
5, 5, and 5.
This is a very easy one.
Yep.
And now I simply just add them. Notice that the electrons here are going to cancel.
Yeah.
5 electrons.
Now, this is my favorite part of doing these is canceling stuff out that's on both sides of the reaction. In this case, it's just electrons. Sometimes you get all sorts of fun stuff and you get rid of it.
You want to get everything to cancel that can cancel. This one's easy in that we only have one thing to cancel. So I'm just carrying down. I brought down the 8H positive. I brought down the permanganate. I brought down the 5 Fe2 positives. And I'll do the same thing for the other side. 5 Fe3 positive plus Mn2 positive plus 4 waters. Now you understand, folks, if this was a guess and check one, you'd be working very hard to do this over and over and over again. And let's do this K2SO4 one now. All right, so I've got K2SO4 plus NaCl makes chlorine gas plus SO3 2-. So what I'm going to do, now this one doesn't have like ions, I just take the K2SO4. I'm going to do this because it's going to turn into SO3. That's the change. The change actually happening, the sulfur is changing its oxidation number. So I'm going to say SO3 2- here. And now I need to balance, what's the rule now?
Well, first we balance the non-hydrogen, non-oxygen things. And I see 2 potassiums that need to be balanced somewhere.
There we go. I've done
Mr. Bergman?
What?
You need a 2 in front of it to begin with.
Oh, yeah, you need 2 potassium.
And these are potassium ions because it's in an ionic compound, so they're just going to stay ions.
Yes, the reason I did this on purpose to make sure you understood this, folks. You can't change the charge of the potassium because the sulfur is the one changing his oxidation number charge, if you want to think of it that way.
Yep.
So I must leave everything else the same. Otherwise, you'll have 2 ups and a down, or 2 downs and an up, or something like that. All right, so we've got all the elements balanced except for oxygen. So I need to add 1 water on this side.
Yep, because you got 4 on the left and 3 on the right, so we're going to have to add 1.
And that creates a problem on the left, so I need to put 2 hydrogens on this side. And now we're going to figure out this whole charge thing. This side has a charge of +2 because of the hydrogens here. The potassium sulfate has no charge. This side has a charge of -2 + 1, -1.
0. That side's neutral.
This side has a charge of 0. So it has no charge, and so I need to add 2 electrons to this side. Okay? And this second one, I have the second half reaction. I've got the salt, the sodium chloride, going to Cl2. Now I need to balance everything. Now again, it's that sodium. I think I've learned my lesson. It's in a positive, not in a positive charge because it is an ion.
However,
look
at your chlorines. You got 2 on the right and 1 on the left.
Oh yes, so I must put a 2 here.
And that's going to change the number
and that makes it 2
of sodiums. There you go.
Now I have to balance my oxygens and hydrogens. But the good news on this one, of course,
there aren't any.
There aren't any O's or H's. So we can just balance the charge. The charge on this side is 0. The charge on this side is +2. So we're going to add 2 electrons to this side. We then simply add the reactions.
Hey, look at that.
Hey, and we have 2 electrons here and 2 electrons here. So they cancel. We do not have to do the lowest common multiple business. And now we just bring everything down. I don't think anything's going to cancel here.
Nope.
2H, except the electrons, of course.
Yep, always.
Plus the potassium.
Potassium.
The potassium sulfate.
One note about that is if your electrons don't cancel for some reason, you did something wrong. Okay. So like if both of your electrons end up on the same side of the reaction, you did something wrong. You got to start all over. All right? So be careful with that.
What did I miss
Sulfite, potassium ions, and water.
That says 2 minus plus 2 potassiums plus water. Now, how do you know if you've gotten the reaction correct?
Well, there's a quick and easy way. Well, two ways. Well, you could go and count every element, make sure they're equal numbers on either side, and that's fine. You can do that. Or you can go through and just make sure the charge is the same on both sides. If the charge is the same on both sides, you probably got it right.
So this side has a charge of plus 2.
Mm-hmm.
So this charge is 0 plus 2 plus 4 minus 2 is
Plus 2. Ta-da.
If you get the charges right, then you're probably very good.
Yeah, you're going to be pretty hard pressed to get the charges right and not get everything else right.
You know, this particular problem, I think we've done enough of these examples.
Yeah, that one probably is going to show up in your homework. That is a classic redox problem.
Okay. Now, what happens if you have a basic solution? The basic solution, it actually is the same exact series of steps, except for you add a step 5 and step 6 right here. These are inserted. It's the exact same steps. You're going to add hydroxides. You're going to sort of assume it's an acid solution. And once you assume it's an acid solution, you're then going to add some other things. So this should not be terribly difficult. So let me see if I can recopy this one, because I think the black screen makes it just a tad bit hard to read. So the aluminum plus the permanganate. Now this is in a basic solution.
Yep.
Where the pH should be what?
Greater than 7.
This is an interesting compound, AlOH4 negative. That's called a...
That's a complex ion or coordination compound.
You learned that in the last deal here. Right? All right, so let's do our permanganate first.
Yep.
All right, so the permanganate is turned into, we call it manganese dioxide. So MnO4 negative turns into MnO2. So now we're going to apply our rules. So the rules that we've done before are the exact same rules. Balance everything but H's and O's.
Okay. Manganeses are okay.
We're good.
Manganeses?
Manganeses?
Manganese?
Manganese.
I don't know. All
okay.
right.
So we're going to say 2 waters on this side.
Yep.
Because I need 2 extra O's.
Now we do
That creates an
hydrogens.
H problem, and that's 4 H's. Now, of course, but this assumes it's an acid, and we just said this is a base. You can't have H's when you have an acid. So
No.
what's the next step?
So now we go to, we have to cancel out the hydrogen ions with hydroxides.
So I'm going to add the exact same number of hydroxides to both
sides, just like algebra. What you do to one side, you do to the other.
It's an algebraic thing.
Yes, my algebra teacher beat that into our skulls.
That if you have 4 hydroxides mixing with 4 hydrogens, you will make
4 waters. It's
4
a
waters.
neutralization.
So this essentially goes away right here, and this becomes 4 waters.
Yep.
But if you also make a note here, I have 4 waters here, and I have 2 waters here. What does that do?
Well, we can cancel out 2 waters from both sides.
So the 2 waters on the left side goes away,
Yep.
and 2 of the waters go away here, and so this now becomes 2 waters on the left side.
Yep.
Now we have everything balanced.
Except for charge.
Except for charge. So let's watch the charge here. The left side, if you add that up, there's a 0 charge here, a -1 charge here. So that's -1. 0, and then -4. So I need to add additional
3
electrons on the left side. So I'm going to say 3 electrons on the left side. This would be best if you had a wider piece of paper, and I'm running out of space.
Just as a side note, guys, if you put the electrons in before you do the hydroxide thing, you're still going to get the same answer. You can do the hydroxides first and then balance the charge, or you can balance the charge with the electrons and then do the hydroxides. It's going to come out in the wash.
Now, the second half reaction is actually easier than the first. You could do the method that we just did, but frankly, if it's in a basic solution and you have hydroxides, and hydroxides are something you're allowed to sort of play with, where could I put hydroxides to balance this
Put
out?
4 of them on the left.
I could essentially just put 4 hydroxides on this side, and that is balanced short of the charge. And so now I can play the charge game. The charge on this side is -4. Charge on this side is -1. And so I need
3 electrons on the right.
Electrons on this side.
Oh,
Again,
look.
We have picked a 1. Almost probably shouldn't have, but we have picked a particular problem where the electrons are the same on both sides, so they go away, and we simply just bring things down. Now we need to also take a look carefully and see if anything else might cancel out. I've got waters on this side, no waters on this side. But if I have 4 hydroxides here and I have 4, then they both cancel out. So if I bring whatever's left over, I've got the 2. I may change colors. This is going to get us confusing here. I've got the 2 waters. I'm going to bring down the permanganate, and then I'm going to bring down the aluminum. And then I'm going to make the MnO2 plus the Al, the complex ion, OH4 negative,
And that's it.
I believe that's it.
Yeah.
All right.
Now I know this next one, the electrons do not even out.
So this is a little trickier one. Okay. All right, I've got Cl2. Actually, I'm just going to start at the top here. You've got, it's this reaction right here. And so I see that the chlorine is turning to ClO negative.
This will save us some space here.
I'm looking for space. Cl2 goes to ClO negative.
Yep.
All right, so I need to balance everything but the
oxygen, so put a 2.
2 here. And now I'm going to balance the water with, or the oxygen with water, put H2O on this side. And that I need to have 2 of those because of the, now watch this, there's a 2 here. And a lot of people make that mistake. And then I'm going to add 4 hydrogens on this side.
Yep.
Now I'm going to add
we've got to do the hydroxides. That'll work too.
Solution,
yep.
So I need to add the 4 hydroxides to both sides.
I always do the charge first. That's why. That's right. Works the same way either way.
Okay, and this becomes 4 waters.
Yep.
And there's 2 waters here. So these waters go bye-bye. And these 4 waters become 2 waters. Now I need to balance the charge. The charge on the left is -4. The charge on the right is -2. So I'm going to need an additional 2 electrons here. Okay.
All right, potassium permanganate.
And I have potassium permanganate, so that's KMNO4, and that's going to turn into
MnO2.
And actually, we've done this one before, sort of.
Yep, sort of.
All right, so I need to balance everything except for the O's and H's.
Yep.
So I have this K.
Got to put a K on there. Yep.
It must be K positive because the substance that's changing its charge is the manganese right here.
There's one of each on both sides, so that's fine.
So now I'm going to add
2 waters on the right to get those oxygens to balance.
On the right. That then needs 4
hydrogens.
Now we're going to add 4
hydroxides
to this side.
Both sides.
And then this is 4 waters right here. And so these 2 waters go away. Each problem we've had has been sort of 2-4. They don't always that way.
Not always.
I put 2 waters on this side. And now we need to do the charge.
Yep.
So the left side has a charge, I think, of nothing.
Nothing. That one's neutral.
Charge, and this side has a charge of -3.
Yep. So we need 3 electrons on the left.
So I need 3 electrons on the left. Now this is getting kind of confusing.
Yeah.
Because we have lots of things going on.
Let's do a rewrite.
I'm going to rewrite these reactions, so I think it's a little easier to rewrite it. Sometimes this is good to do a rewrite. So to the 4 hydroxide on the left plus the chlorine, I'm just bringing down reaction number 1.
What kind of accent was that, Mr.
I don't know. It is my interesting reaction accent.
Reaction accent.
You heard of that, right? No? No, I don't either, because I make up.
Yeah.
Okay. And then we now have
it's like
second
part
half
Scottish, part French, part Russian, part I don't know what it is.
What happened into my brain? It's so silly.
But don't forget your electrons.
KMNO4 negative, and I forgot my 3 electrons. I should have. I'm trying to center, and I probably needed more space on this one. Oh well. MnO2 plus K positive plus the 4 hydroxides. Is that a good third?
Wonderful. All right.
Now I have 2 electrons in the first reaction and 3 in the second.
Yep.
So what's the common multiple in 3 and 2?
6.
So I need to make this 6. To make this 6, I think green will be our color. I'm going to need to multiply this reaction by
3.
So this 4 becomes
12.
a 12. This becomes a
3.
This becomes a
6.
This becomes a 6. And this becomes 6. And we'll choose a green works too.
Yeah.
Multiply the second one by
2.
So this becomes 6.
6. 4. 2. 8.
8. And now we're going to add them. But we do have an issue when we add them. Is that not only do the electrons cancel, 6 electrons cancel here, and they cancel here, but I also have
waters and some water.
All right, yeah. So let's do the hydroxides first. I have 12 hydroxides here, and 8. So the net effect is I'm going to have
4 hydroxides.
4 additional hydroxides on the left. Let's put the arrow here. And then on the hydrogens, or the waters, pardon me, I have 4 waters on this side and 6 on this side.
So we're going to have 2.
I'm going to end up with 2 waters on the right. And then we sort of just fill in
put everything else.
I'm going to bring the chlorine down, so that'd be plus 3Cl2 plus, here we have 2KMNO4.
I think it's all going to fit.
I'm trying to make it all fit, yes. And then that's going to turn into, what do I write?
6 hypochlorites.
ClO negative plus
2 MnO2s.
MnO2s.
And 2 K pluses.
2 K positives. Now that's a complex problem, but that, folks, is essentially it. And so I think we need to continue. I've been working on this, and what do you think? I'm going to get the...
You've been working on what? Playing the spoons? Let's just use spoons to put food in our mouths. Isn't that what they're for? Should I break out the washboard and get a little hillbilly band going on here?
Have you ever heard a guy who plays the washboard who's really
Get a big old jug. I don't know. Alright. We'll see you in class, guys. Bye-bye.